So we can wrap up chapter one with this last video here, and we're going to talk about interpreting data. So let's enlarge this slide here. So this skill about analyzing, interpreting data either in graphic form or in table form is an important skill to have. So say we have, data that we're collecting. It could look like this. We could have samples A, B, and C here. We could include a mass of our water sample. So overall, we have 20 grams, 50 grams, 100 grams in our sample size. In the middle column here, we have the mass of hydrogen gas that could be formed if we pass an electrical current through our water sample using this process of electrolysis. We could generate O2 and H2 gas, and then we could collect these masses at the end after they separate into H2 and O2 gas. What we can see here is the sum of the masses of both the oxygen and hydrogen always equal the total mass of the water sample. So 17.8 plus 2.2 gives you 20, 44.4 plus 5.6 gives us 50, like so. So do you see some patterns here? Well, you may. We can see that there's always a very similar mass of oxygen to mass of hydrogen ratio here. So if we were to divide the mass of oxygen, remember that 17.8 to our 2.2, we get about 8.1 here. In the middle column, B, or in the middle row rather, we see that ratio is about 7.9. Again, 44.4 divided by 5.6. Then we have 88.9 divided by 11.1, and we get another ratio of 8. So we might have some experimental error that could explain this, but we can see that we always get the same ratio. When we look at graphs, we usually want to know what is our independent variable, which will be on our x-axis, versus our dependent variable, which will be along our y-axis. So we're noted here that scientists are always observing graphs to kind of see trends in data. That's what we're referencing here, this rising value for CO2 gas. So we see that graph here and these kind of exhilarating trend lines here, where we go from early mid 1800s rather, and we can see the CO2 along the y-axis versus the year along the x-axis. So our independent variable would be our x-axis, which is our year, and then the CO2 production, atmospheric carbon dioxide gas would be dependent on that. So that's our y-axis. All right, so we have our independent variable on the x, our dependent on the y. So if we wanted to read this graph, we would look for the intersection here, say, of 1860 with that line. So we're well below 290 here, the concentration in parts per million. So that's million parts of air molecules. There's only 290 carbon dioxide molecules per million parts. But that is almost doubled, right, throughout our history here, up to 2020. So we can interpret this data. We can see that there's a rise. We can see that there's an increase over time. Uh, the y-axis does not begin at 0. If we began it at 0, there would be a lot of empty space between 285 and below, because that's when we started recording our data. So depending on the parameters, the time frame of your data collection, you might shift your scale. There also could be different units, different increments that are used that all kind of dictate the best way to present your data. Um, so we can see that the increase in CO2 has not been consistent over time. We don't just see a horizontal or diagonal, rather, line that goes from, the lower left corner up to the top right corner. We can see more of an exponential type of growth. This increase in rate of production really, skyrocketed, maybe around the 1920s and beyond. But that probably coincides with, our human activity. So, it's good to know how to interpret data, either in graphic form or in table form. So we'll be looking at this more during our laboratory procedures, and actually collecting data and analyzing it together.